All right, so again, we're continuing on with energy. Tying it all together, I guess more so, is that we're looking at what's called the law of conservation of energy. And this kind of comes back to that last example I did in class earlier today. And the key here is that energy in a closed system, I would say, in a closed system, energy is neither created or destroyed. So the energy you have before something happens is equal to the energy you have after. So an example of a closed system was, again, the last example that I did earlier today, where we had a tree branch that had nothing but gravitational potential energy. It falls to the ground, and so all that gravitational potential energy has now been converted into kinetic energy, all of it, because, again, the law of conservation of energy says it can neither be created or destroyed. So what you start with is what you end. Nothing more, nothing less. All right, so I want to do a couple of examples, again, going over the conservation of energy. So again, I have my lesson here. Hopefully you have it in front of you, where we're talking about a hockey game. So during a hockey game, bad English here, somebody shoots the puck, which is 0.168 kilograms into the top corner of the net. Nice. Which is 121 centimeters high. If the puck leaves the stick traveling at 120 kilometers an hour, at what velocity does the puck enter the net? Assume there is no air resistance. All right, so again, I always, with word problems, I like to read the question at least a couple times, but read it once. The second time, I'm going to get my information. All right, so during a hockey game, the player shoots the puck, and its mass is 0.168 kilograms. So there's our mass. And it's in our standard unit. That's a good thing. All right. And then it goes top shelf, right into the corner, which is 121 centimeters high. All right. So my height is 121 centimeters. That's the change in height. You can call that delta H. Or in this case, the puck was on the ice. Up it goes. So it is H or delta H. Again, not in our standard unit. So to go to meters, divide by 100, that would be 1.21 meters. All right, so now we continue on here. If the puck leaves the stick traveling 120 kilometers an hour, so I'm going to call that my V1, my initial velocity here, which again is 120 kilometers an hour, which again is not standard units. And so if I'm moving from kilometers to meters per second, I have to divide by 3.6. All right, so if I take 120 and I divide it by 3.6, I get, again, two decimal places, 33.33 meters per second. All right, assume, at what velocity does the puck enter the net? All right, so that I'm going to call as my VF, I guess, the finale. We don't know. All right, now again, I'm going to use the law of conservation of energy in that your energy at the start, or E1, or EI, E1, however you want to look at it, is equal to EF, your final velocity. So we have our initial velocity, our initial energy is equal to our final energy. Now, in the very beginning, it has no gravitational potential energy, the puck, because it has no height. If you have no height, you have no gravitational potential energy. But it does leave the stick from the ice going very, very quickly. And so we have kinetic energy to start off. So I'll call it EKI or EK1 because it's at the very beginning. So we have that kinetic energy at the beginning. Now, when it hits the net, the top shelf, it has both. It is moving, so it has kinetic energy, and it also has height, so it has gravitational potential energy. And so we have two types of energy in the end. We have our, like I said, our kinetic energy, which I'll call EKF, and plus our EGF, our gravitational potential energy at the end. All right, so plugging in or substituting in our formulas here. So our kinetic energy is going to be mv squared, or in this case, mv1 squared, divided by 2. All right, kinetic energy Let's see here, our final. Again, this time we're going to have mv squared divided by 2, but it's going to be mvf squared, our final velocity. Now, let's see, what else we got here? Our gravitational potential energy, where we have our m times g times our h, or delta h. In this case, because it started on the ground, it's just an h. Again, doesn't really matter as long as you get your values. Now, here's a little bit of a trick. Here I did this substitution. And Ray, you're going to love this because this is one of the very few benefits of using your equation first. I have an m, and I have an m, and I have an m in every single term. So that means I can divide everything by m, which means this m is gone, this m is gone, and this m is gone. I divided everything by m. I got rid of the m's. So in other words, mass doesn't even matter in this situation. Not a bad little trick to do. All right, so now I can substitute in. So again, my v1, the initial velocity is 33.33 squared divided by 2. All right, I don't have, again, no gravitational potential energy initially. Let's see here. Over here I have vf. That's what we're trying to find. So vf squared divided by 2. And then plus g times h. So that's 9.8. And we went up 1.21. Okay. Now, to simplify things, let's see here. I can do 30. Again, you got to follow better, so make sure you do the exponents first here. So 33.33 squared. Then divided by 2. I'm getting, whoa, nice number, 555.44. All right, again, we have vf squared divided by 2, plus this thing here, I have 9.8 times 1.21. That's got to be like 11 something, I'm thinking. 11.86. Okay, so now I'm going to get vf by itself here, right? So I got quite a few things to get rid of. I'm going to move this 11.86 to the other side. And so essentially it's going to be subtracted from 55.4 or 555.44. And so if I subtract 11 from that number, I get 543.58. And that is now equal to VF squared divided by 2. A lot of ways you can do this one. I think the most simple one, I've done this many times. I have a number equaling a fraction. I like to always create fraction equaling a fraction. That way, again, I can cross multiply and get rid of all the fractions. So I have 1 times VF squared. Well, that's going to be VF squared. And then I have 2 times that 543.58. So it's going to be 1,000. Let's see here. I'm going to have to grab a calculator. And I get 543.58 times 2. I get 1,087. Again, going to 2 decimal places, 0.16. And of course, to get rid of the little 2, right, the squared, I have to square root both sides. And when I square root both sides, I get 32.97 meters per second. So even though the puck was shot with 33.33 meters per second, because it's on its way up, it loses some of that kinetic energy, and it takes a little bit off the shot. So it just enters the net a little bit slower. This is the case, not this year, but if you ever are a hockey fan and you watch the NHL All-Star competition and you look at the hardest shot, what players will do, now they don't know why they're doing it, is my guess, because most of those guys didn't finish high school, is they shoot the puck along the ice because they don't want to see this little bit of a drop that could cost them the competition. So usually the winner is the person who shoots in the bottom half of the net, reducing the amount of kinetic friction or kinetic energy that's lost. All right, so now another reason to shoot low if you're a hockey player, because I coached hockey for like 15 years, is that your legs move half as fast as your arms, reaction time wise. So that's another reason why you would shoot low. You reduce the amount of kinetic friction or kinetic energy lost, and you maximize the fact that the goalie can't move his feet as fast as his arms. All right, little kinesiology there for you folks. Example 2, the old roller coaster. Okay, so this is what a lot of people don't realize is that roller coasters do not have a motor. It's all gravitational potential energy that's used. That's why the big drop at the start. All right, and that is converted into kinetic energy. That's how a roller coaster works, reducing friction. All right, so example 2. Many roller coasters have loops where carts roll on a track that curves sharply up into the air. And the roller coaster shown that I've got, the cart must have a minimum speed, because you don't want to be caught at the top, of 10 meters per second at the top of the loop to make it around safely. Assuming the roller coaster starts from rest, which basically does, right? That's why it creeps, at the top of the first hill, and there's no friction. Okay, so we're making a little more simple situation here. What is the minimum height of the first hill? All right, very important. So let's see here. So we have our diagram here. Again, hopefully you're looking along here. There's our roller coaster. So we want to know the initial height. So again, looking at the conservation of energy, where we have our E1 is equal to EF. Energy before equals the energy after. All right, so at the very top, all right, we have no velocity. Whoops, question mark, 0. That height of that first hill, whoops, why am I mixing these up, is a question mark. All right, we don't have the mass of this roller coaster because it doesn't matter. Now, afterwards, on my diagram, the minimum speed, it says, is 10 meters per second. All right, and the height of that first loop, we're told that height of that first loop, which I'll call H2, is 16 meters. All right, and I believe that's all the information we have. All right, so now, using the conservation of energy. Now, initially, at the top of that very first hill, that's what we're talking about here, there's no speed, so there's no EK, all right? But what we do have is some gravitational potential energy. All right, now that gravitational potential energy is released and we get some speed, so we've got some kinetic energy, but then we go up the loop. Now the loop, we're going to have both speed and height. So we are going to have gravitational potential energy, so I'll call it EGF, plus kinetic energy, which I'll call it EKF. All right, so what does that mean? Well, again, I'm going to make that substitution here. So our initial gravitational potential energy will be mass, not changing. G doesn't change either. Height 1 matters, all right? EGF, well, again, we have M, G, and H2, our second height. Plus, now we have kinetic energy because we're ripping around that loop. And so I have M VF squared divided by 2, or 1/2 times MVF squared. Same thing. All right, so again, this is a shout out to you, Ray. I have an M in every single term in this equation, so I can divide every term by M. That's hence why they don't weigh you when you get on a roller coaster, because it doesn't matter. All right. Now, substituting in. G, always 9.8 when we're on Earth. Close to it anyways. H1, that's what we want to know. How high does that first hill have to be? All right, now we have G times H2. Well, again, G is 9.8. H2, the height of that first loop. I was thinking about the dragon fire when I wrote this question on Canada's Wonderland. Is 16 meters. Plus, I'm going to go with the 1/2. 1/2, I guess I'll leave it. VF squared, what's our velocity? Has to have a minimum of 10 meters per second. All right, so I got 10 squared, and of course divided by 2. All right, so now it's all about simplifying and then solving for H1 here, our height of our first hill. So I have a 9.8 H1 9.8 times 16. I don't, let me see here. I get 156.8. All right, plus, let's see here. Well, 10 squared divided by 2. 10 times 10 is 100 divided by 2. We get a 50. All right, so again, moving on here, I get 9.8 times H1. I put 156.8 plus 50. That's going to be 206.8. All right, and then our last step, we're going to divide both sides by this 9.8. And so we're going to find the height of that first hill, H1, which is equal to 21. Again, go to 2 decimal places, 0.10, and we're in standard units, and so it's meters. And that is the type of things when they're building a roller coaster, they need to know specifically how much energy they have on top and what speed they need to move around that curve so that we don't have an accident. Now, there's obviously other factors that engineers take into account, like friction between the wheels and the track. You're losing energy, heat energy, which we will, well, I don't think we're doing heat, but we might. I can't remember now. Heat energy is lost because of friction. You have the force of wind resistance. Those are all the type of things that they do encounter when they build a roller coaster. They have to account for everything, right? Because we don't want accidents. All right, so that is it for today in the law of conservation of energy.